Linear inequalities are the study of straight line graphs, but they have shaded regions in them called feasible regions because you're not just equal to the line, you're less than or equal to, greater than or equal to, less than or greater than the line itself. So this is the study of how those lines interact with each other and how to use this to solve problems. So we're going to go through two word problems today together. The first one is this one. A parkade can fit at most 100 cars and trucks on its lot. A car covers 100 square feet and a truck covers 200 square feet. The lot space is 12,000 square feet. It charges $20 per car and $35 per truck to park these vehicles each week. And how many will bring in the maximum revenue? So the first thing I like to do is take a pen or a highlighter or something and go through and highlight groups of information. So at most 100 cars and trucks, that's an important piece of information. The square footage for each thing, that's important, and it's all kind of grouped together. The square footage goes together. And then you have the cost of each item, or what they're charging each item. And we know that they want us to have a maximum revenue. So that's what I'm trying to find. So I need to set up my variables. I'm going to have R for revenue. I'm going to have an X, and I'm going to have a Y for my graph. Now in this particular case, my X and my Y, it looks like I've got cars and trucks for the number that I can put on, and I've got cars and trucks for the square footage. So it looks like my X and my Y are going to be my cars and trucks. I look to see what's repeating in each section. So now I need to get my equation. My objective function is the function that will maximize my revenue. So objective your objective is what is the point of the question? What's the object? What's the objective? Well, I want to find the maximum revenue in this case, so my objective function has to do with revenue. So my revenue, and the thing here up here, the color that up here deals with price is yellow. So $20 per car, and cars were X, plus $35 per truck, which was Y. That function right there is an important one that you'll be using at the end of the question, but you've gotten rid of that information out of the question and you're not going to use that again. So we've got to make an equation for the blue section and an equation for the pink section. The blue section says I've got at most 100 cars and trucks that I can fit on the lot. So that means my number of cars plus my number of trucks has to be less than or equal to 100. I can't go over 100 cars and trucks together. Then I've got to do an equation for the pink section, and it's about square footage. So 100 for every car plus 200 for every truck, and 12,000 is my total, but I'm not going to be equal to my total. I have to be less than or equal to that total. That equation can be simplified. I can divide everything by 100 to make things easier, to 1x plus 2y less than or equal to 120. It just makes it easier to graph if you simplify it. Gives you the same equation. My next step is to take these equations and put them on a graph. Well, in order to do that, it's useful if I have my x and my y intercepts. Here, x-intercept and y-intercept for my x-intercept, I set y equal to 0. So if the y is gone, x is equal to 100. And if I go for my y-intercept, I set x equal to 0, so y is equal to 100. Down here, if I set y equal to 0, x is 120. And if I set my y equal to 0, or my x equal to 0 to get my y-intercept, y is going to be 60. Good, now we can go ahead and graph these points, but the reason I did all that work is because I want to set up my graph equations here so that I've got enough points to cover my x and my y-intercept. So I got to get to 120 is my biggest x, and 100 is my biggest y. So going along here, I can probably skip by tens. So 20, 40. Remember, you don't have to put every single tick mark on the graph when you do it. Just enough so that the person reading knows what scale you used. And you don't have to use the same scale in your x and your y. Okay, so I've got my graph grid set up. Now I can put my lines on. So both of these lines are going to be solid because I've got an equals in both equations. So they're both solid lines. The first line goes from x equals 100 to y equals 100. So from 100 to 100. There's the first equation. And the second one goes from 120 in my x to 60 in my y. So I'm going to take a highlighter or a colored pencil or different colored shading, and I'm going to go back to my original colors that I used up top. So x plus y less than or equal to 100, well, that's this line that I put on first, and less than 100 is going to be down here. And then this one is also less than, so it's going to be underneath here, and you can see where I'm double shading. And I've actually got two other equations that I'm not using so much, but I'm kind of implying them, where my x has to be greater than or equal to 0 and my y has to be greater than or equal to 0, because you cannot have negative number of vehicles. So I've got a restriction here and a restriction here that it's got to be in this region. So my next question that I need to ask is this data discrete or continuous? Well, my x and my y deal with the number of cars and trucks. Does it make sense to have a decimal number of cars and a decimal number of trucks? No, it doesn't. I either have the car or I don't. I don't have 0.2 of a car. So this region down here has to be stippled. So you have to have dots in the region to show that you don't have to put absolutely every single dot in, but you have to have dots in there to show the reader that not every value will work. Only certain whole number values will work. Because your restriction is you cannot have negatives and you cannot have decimals. You won't always have to put that stippling in, just in the cases where your data is discrete, where you can't have decimals and fractions. So my next step then is to pick off I'm going to scroll down some to give myself some room. We have to pick off the corners. So I've got one corner here at 0, 0. I've got another corner here on my feasible region at the 100, 0 point. I've got another corner here at the 60. And I've got another corner here at 80, 20. So what do I do with all of these? Well, I take them back up into this very important equation that we had at the beginning. And I put these numbers in that equation to see what I get. So I put 0 for x and 0 for y. So 20 times 0, 35 times 0, that gives me $0 revenue. Well, that's definitely not going to be my maximum. Then I go for my 0 or 100 and 0. If I put that in there, 20 times 100 and 35 times 0, that gives me $2,000 revenue, which is not too bad. If I put the 0.60 in there, 20 times 0 plus 35 times 60, I'm going to end up with 2,100. And if I put the last point in there, 20 times 80 plus 35 times 20, I end up with $2,300. So I go back to my original question. It says which combination will give us the maximum revenue. So selling or keeping 80 cars and 20 trucks. Gives the maximum revenue. So that right there is your final answer to the question. Now, it's important to remember, you have to check all the corners of your feasible region. You cannot just give me one number as an answer and say the 80-20 is the maximum. Well, if you only have one number, then it's definitely the maximum of all those numbers that you gave me because it's the only one you gave me. You have to show, using the corners of your feasible region, that you have the maximum. Stating one point is not going to be enough. You have to prove it's the maximum of all the vertices. Let's try another example. This one's a little bit more complicated because there's more information given. But again, we're going to sort it by color. So I'm going to grab a highlighter. Start with yellow this time. We've got nitrogen. We've got phosphoric acid. And we've got potash. And we've got money. So what quantity are we trying to maximize so we can get our optimal equation here? What's our optimizing function? Go back to my pen. We are trying to get cost. So cost, and my cost equation is going to be 22x plus 18y, where x is brand A and y is brand B. Then I have to come up with some equations. So for my equations, I'm going to have 3 of them this time. I'm going to have nitrogen, phosphoric acid, and potash. And I'm going to get the information I need out of this table. So for nitrogen, there's 30 in brand A, which is X. There's 20 in brand B, which is Y. And according to this, it needs at least. So that means it needs to be greater than or equal to 120 kilograms of nitrogen. Phosphoric acid, same idea. 2 from brand A, 4 from brand Y, at least, so it needs to be greater than or equal to 16. And the potash, 1 from X, 4 from Y, at least, so it must be greater than or equal to 12. And we also know that X and Y have to be bigger than or equal to 0 because it doesn't make sense to have a negative number of kilograms. So we go for our X and Y intercepts now. In this equation, if I set Y equal to 0, if I get rid of my Y, then my X is going to equal 40. And if I get rid of my X variable, Y is going to be 60. Down here, my X-intercept would be 8. My Y-intercept would be 4. And in this one, my X-intercept is 12. And my Y-intercept is 3. In this case up here, it might actually be easier to graph if you got rid of the common factor here of 10 and made it 3x, 20y, 120, which makes it 4 and 6 for our intercepts. So you can always look for common factors. You can do the same thing in here. There's a common factor of 2 as well. But because those numbers were quite big compared to the others, I'm going to cut those down. I'm going to go grab a ruler, set up my axes. There they are. Now I need to get to at least 12 in the x direction and at least 6 in the y direction, so counting by ones is probably going to be enough. 2, 4, 6, 8, 10, 12, 14, 2, 4, 6, 8, 10. Again, you don't have to label every tick mark, just enough so that whoever's reading the graph knows what you wanted to have for your points. So if I grab my ruler, I'm going in the first one from 4 to 6, 4 in the x direction to 6 in the y direction. There it is. And my next one, I'm going from 8 in the y direction, x direction, sorry, to 4. There it is, and you can see where they're crossing. And then I need from 12 in the x direction to 3. Okay, so we've got an interesting sections going on here. Go grab my highlighter again. Yellow was nitrogen. That was my first equation that I put on there with the 4 and the 6. And it has to be bigger than, so it's on this side of that equation. Green, phosphoric acid, was the second equation I put on, and that went from 8 to 4, so that's this one. It has to be bigger than. So you can kind of see where the region is shaping up to be. And the last one was blue, and it went from 12 to 3, and it was also bigger than. So you can see that the feasible region, I'm going to get rid of all the extra stuff that I wrote in. You can see that the feasible region is this section up here on top of the graphs. So this whole area up here, and it has to be bigger than 0, so it can't go negative. That means I've got 4 corners to test again. Does this region need to be stippled? In other words, does it make sense to have decimals and fractions, or is it discrete? And the answer is no, I don't have stippling this time because my data is continuous. It's not discrete. It makes sense to have decimals and fractions this time because I can have 1.5 kilograms of nitrogen, and I can have 6.5 kilograms of phosphoric acid, and I can put in half a bag of brand A. I don't have to put the whole bag in. So it makes sense to have fractions and decimals this time, so I don't have to do this to my graph like I did last time, because it's a continuous graph. Continuous means it makes sense to connect the points. Okay, now we need to get our corners. There's one here at 2, 4, 6. There's one here at 2 and 3. There's one here at 4 and 2. And there's one over here at 12, 0. So I have to test each of these in that equation that I had put up at the beginning, because I'm trying to find out the cost. So if I put 0 in there, 0 plus 18 times 6, I'm going to get $108. 2 and 3, 22 times 2 plus 18 times 3 gives me $98. 4 and 2, 124. If I put that into my equation, so 22 times 4, 18 times 2 gives you $124. And if I put 12 and 0, 22 times 12, and 18 times 0 is 264. So I wanted to minimum cost. I wanted to minimize it. So I'm looking for the smallest, which is this one. And again, you can't tell me it's the smallest unless you've got something else to compare it to. It can't be the smallest of one set of numbers. You have to compare it to all the other corners. The minimum cost is $98 when you use 2 bags of A and 3 bags of B. You always have to go back and interpret what your answer is telling you according to the question. It's got to go back to the question at the end. So you always need to have that concluding statement. So that's a quick review of linear inequality word problems. I'm hoping that helps you out some, and if you have any further questions, please contact me in the AC classroom.